No, we have a quiz. It's right here. All right. Let me see. Make sure we have everything here. Homework. Any questions? No questions? Everything's going well? Everybody look at the grades? They're great. All right. So this is ee420 / ecg. Is there a question back there? Stephen, Jonathan, thank you. No, it's our sound in this room's a diode. It can only go in one direction, from you to us, not backwards. What lecture is this? February 2nd, 2015. All right, so what I want to do is I want to get through example 9.5, and then I want to talk about, I think it's gain FT product. Let's find out. Small signal model, transition frequency. All right, gain FT is kind in this and this. There was a email, Kobe. Did you get your question answered? So let's talk about that real quick, shall we? So that problem, what number was it? So one of the issues that I'll show you right now, you're late. So it's this one right here. All right, so let's go look in the LT Spice folder here. And let's see, where's a good example? Like this one maybe? No? This one? Okay, so this one, let's change this to 1 volt. Okay, and then I'm going to, what's VDS? 0 to 5. I'm going to go ahead and run this sim, and then I'm going to determine what R out is from the sim so I can see how it matches my hand calculation. Okay, so I run the sim, and I see that there's my output current. It goes up, and then the slope of this, 1 over the slope is. So I take the derivative of this, and I take 1 over the derivative, and I get R out, just like it said in the schematic right here. Plot ID, and then 1 over the derivative of ID to get the R out. And I look at my value, and it goes from roughly 5 meg up to 11 meg, so more than 100% variation. So what did you use for your hand calculated value for R out? What was the value you used? Okay, so if it was 8 point whatever, and you were operating at a smaller voltage, say down over here, could be way off, right? So this tells you what the output impedance is for a specific operating condition. And then once you've determined that, you can go and it'll be precise. You can go look at this plot and go, I used 5, a better approximation is this, or I used 8, which is out here. Better approximation is 5, but 8 is a good value for being in the ballpark. Does that make sense? Well, wait, that's okay. Maybe I'm jumping the gun here. So let's go back and let me sketch the schematic. So once we have our output resistance, you have a AC source here of 1 millivolt, right? Then you have a R out, which is the MOSFET, drain to source. Now we're doing our AC schematic, right? And then we also have 100K between the drain and AC ground. And what's AC ground here? What was this 100K connected to in this problem? VDD, but I can't change the value of VDD. It's fixed. It's a fixed DC value. So for AC, it doesn't change. That's 0. So this was VDD. If you plot the current that flows through here and you know what the DC operating point is, then this current here, ID, well, what's the voltage here on the drain through the capacitor? 1 millivolt. So it's 1 millivolt divided by R out. Okay, so if I have 1 millivolt, let's just say it's 10 meg is R out, right? So I get 10 to the minus 3 all over, if R out's 10 meg, that's 10 to the 7. So that gives me 10 to the minus 10, which is 100 picoamps or something like that. If I did the math right real quick in my head. So that's why I was assuming when you talk about R out, you know to go to this step. Did anybody not know to go to that step? Any questions? What was the number you simulated? 300 pico? Well, but I mean, if I change this value to 5 meg or whatever, this becomes 200 pico. Well, wait. Okay, so this is very straightforward. You understand this part, right? 1 millivolt divided by R out. Now, if I go back here and I look, my R out's varying from 4.5 meg up to 11 meg, right? So that's 200% variation. So depending on what my drain to source voltage is, if it's here, I'm going to get more current flow because I've got a smaller resistance than if I'm over here. No? Okay, if that's the case, then perhaps your dot include CMOS models got corrupted, so I would download those again. It might be using the default values because it won't tell you if it can't find the models in, it's called NMOS or whatever you have here. It might use a default model for the value and then it's going to give you totally whacked out results. Man, I don't know what to tell you, man. It's I don't know. There's probably not a problem with LT spice. It might be user error. All right. Any other questions? Okay, so let's get going on example 9.5. Okay. So I'm not going to go over what we've calculated already, but I want to go over a few things here. What was the things we've calculated already? We've done it twice in each of the last 2 lectures. Yeah, VGS, the DC. And what was the VGS? 1.05. You guys reading the book? Yes? Okay, so this is a 30 by 2. This is a 10 by 2. We had this come down here. We calculated this was 40. We said, okay, we have an AC signal here of a millivolt. We have a DC signal at 2.5 volts. And then we have a voltage here at 2.5 volts. And then we have in each of these what DC current? 20. And then what was the value of the voltage here? DC? 2.5, and we said the VGS are equal, and both are equal to 1.05. So then the source voltage here, DC wise, is 1.45. Any questions? Okay, oops, this is 30. That's 30. So this, you remember the Kp of the NMOS was 120 microamps per volt, and the Kp of the PMOS, what's Kp stand for? Kitchen Patrol? Kp, transconductance parameter, is 40 microamps. We said that V threshold N was 0.8. V threshold P was 0.9. So I've made this one 30 times or 3 times wider, which compensates for the lower transconductance parameter. So because this threshold voltage is 0.9, 100 millivolts more than the NMOS, I can calculate it. It's done in the book, but it'll find out because there's the same current flowing that that's 1.15. 100 millivolts above what the VGS is here. Any questions? Did anybody not follow that? So how would I quickly calculate that VSG? You guys sure you don't want me using PowerPoint? Sitting back there with you in the audience and just using a laser pointer that has real high power. Yeah. I saw a show this weekend where the professor brought in a cassette player and he put it underneath a microphone on the lectern and hit the play button and just sat at the front while the cassette player read to the... And I thought to myself, that's awesome. All right, what do I do to get... Do I know ID? Yes. Do I know V threshold P? I know everything except VSG, right? So I'll write VSG equals, because I'm going to use this over and over again, 2ID divided by KP sub P times W over L. And I write it like this instead of flipping the L up there because this term is what? Beta sub P plus V threshold P. Looking good? And I solve for that and I get, this actually is called the overdrive. And we'll talk more about that in a moment. Why is this thing not zoomed out far enough today? And this is overdrive or excess gate voltage above the threshold voltage. And it's 250 millivolts for both of these transistors, except here this has got a 0.8 volt threshold and this has a 0.9 volt threshold. That's why this is 1.15 and this is 1.05. Any questions? I solved it 2 times, the last 2 lectures. Yeah. I used it for the PMOS. I didn't want to solve that again. It's also in the book, right here. 250, 250. All right, so what do I want to do AC now. Tell me what to do. Actually, why don't we do one more DC calculation? We know every single voltage in this. What's the voltage here? That's 5. This is 1.15. What's this voltage? 3.85. Okay, I love this problem. I love to give you a test on it. Here, work this problem, but like change the current or change the sizes or something, all right? Okay, any questions? All right, let's do one more thing. Let's calculate this voltage. So what's the VSG of this device? 5 volts. So what would you say, which region would you say that transistor's operating in? Triode. It's got a really large VSG. The only way it's not going to be triode is if this voltage is 4.2 or, I'm sorry, 0.9 volts or lower, and it obviously can't be 0.9 volts because this voltage is 1.45. This has to be above 1.45. As we go from the top of the schematic to the bottom, the pressure drops. So if the pressure here is 1.45, the pressure here can't be less. So I'm going to pause because I just said that. I know nobody follows. So I want to go talk about that in a little more detail and prove what I just said. Okay? So let's draw that transistor out. And let's sketch it one more time here. Let's just call this V drain. And what should this node is V source. Notice source in the NMOS is on the bottom, source in the PMOS is on the top. And what's its voltage? 5. And the gate is? And so I know VSD has to be greater than or equal to VSG minus V threshold P for saturation. Looking good? Let's write it out because we're learning. So that's V source minus V drain greater than or equal to V source minus V gate minus V threshold P. What? All right. So then the V sources cancel. I multiply both sides times minus 1 and I get V drain has to be less than or equal to V gate minus or plus V threshold P. But V gate is what? 0, and V threshold P is 0.9. So V drain has to be less than or equal to 0.9 for saturation. That's exactly what I just said. This voltage here has to be less than 0.9 volts, or the threshold voltage, for that to be in the saturation region. Any questions? Okay, so obviously it's not going to be in the saturation. Tell me why. This is already at 1.45. There's no way this can be lower because the pressure drops from the top of the schematic to the bottom. Yay or nay? All right, so I'm going to treat this as it's deep in, to be fast, I'm going to treat it though it's deep in triode, and I'm going to explain to you what that means because it'll simplify my calculation, and then we'll compare it to what the book has using everything, using the full analysis. So I've got, for the triode equation, I have ID is equal to Kp times W over L, no divide by 2, times what? VSG minus V threshold P times VSD. But if VSD is small, meaning the voltage across here, which I haven't calculated, is very little, which means what does that mean? This voltage is close to what? DC-wise is close to what? 5. That means V source to drain. It's an on device. If you took digital, that's a transistor that's on, right? So that pulls it up to 5 volts. And it's close to 5 volts. Now, that's what I'm assuming. I'm going to verify that in a moment. If I do that, VSD is small. What happens when I take this small number, I square it? Say it's 0.1 and it's squared. It's even smaller. So I'm going to say this is approximately 40 micro times 30 over 2 times 5 minus 0.9 times VSD, which I'm going to write as 5 minus V drain, and that's equal to 20 microamps. Did everybody see how I'm simplifying life here? Yay? Okay, so let's see if I can do a lot of this in my mind here. So this would be 20. Those cancel. And then I get 5 minus VD equals 30 times 4.1, which is 120 plus 3, 123. Yay or nay? Okay, and so then I've got an issue here. Oh, it's 1 over that. And so then V drain is equal to 5 minus 1 over 123. And let's see what we got. So 5 minus 123, shift 1x equals 4.99 volts. Let's see what it is using the full calculation in the book. And it is, oh, pretty close. 4.992, and I got I got exactly the same thing. So my assumption that it was deep into triode was good. 4.992. Questions? So I can go back here, and I can say this voltage is 4.992. Yes? Well, you could go back and do it the full way. But I mean, even if you don't, even if you look at this and say by itself, well, if I neglect this thing's pretty close to 5 volts, so it's probably pretty good approximation. But if you don't, if quadratic equations don't frighten you, then you can just do the quadratic. Okay, how do you derive the quadratic equation? Complete the square. All right, little tidbits of knowledge there. Okay, so let's go back now. Before, I want to do one more thing before we do the AC. Let's switch over to the green because I have lots of green here. You guys can see the green color when you print out the notes. It's okay? So. All right. Then just print to black and white. All right, so I've got the following. Plus, minus 5. And I know that this is deep in Triode. I really don't care too much about the DC value here, but I want to replace that with a small signal resistance. This goes to AC ground. I can't change the DC voltage there. And I'm going to call this R channel, and we derived this a couple of times. You might even have done it in a quiz. I don't recall. What's the R channel then for that device? 1 over Kp times W over L times VSG minus VTHP. Let's calculate that real quick. That is 40 microamps per volt squared times 30 over 2 times 4.1. Here's where a lot of times students will make mistakes, because in the schematic, if you look at the schematic, all the NMOSs have 1.05 volt VGS, and the PMOS has a 1.15 volt VSG. So here, you're physically holding it to 5, so it's a little tricky. So I go through here, and let me just do the math real quick in my head here. So this would be 15 times 40 would be 600. 600 times 4 is 24. 1 over 2, 4, 60, if I did it right, something like that, microamps per volt. Or if we went milliamps, it would be 2.4. And let me see, that's about 500 ohms. 400. Shift 1x. Oh, 400, thank you. 420. What's the book have? 407. Ah, close enough for me not doing any math. All right, any questions? Okay, I got a couple questions. We calculated this last time. I know there's 20 microamps flowing through there, and I know VSG is 1.05. What was the GM of the NMOS? Well, no, okay, no one remembers. It's Kp times W over L times 1.05 minus 0.8, which ended up giving us what? 150, if I remember correctly. Yep, 150 on the bottom of page 283. We've gone over this already as well. Any questions about that? What about for this PMOS? What's the GM of it? We got a current flowing through it. Is it in saturation or triode? What did I say to burn into your brains? There's a current flowing through a device, and its source or drain and gate are at the same potential like it is here. They're tied together. What region is it in? Saturation. There's no current flowing through it. It's off. It can't ever operate in triode. It can either be off with no current or in saturation with the gate and drain at the same potential. Remember, I did that. I went through and I said we're going to use this over and over and over again. It's the part of a current mirror. So it's in almost every analog circuit we're going to analyze. Okay, if I look at that, Kp is 3 times smaller for the PMOS. The W over L is 3 times larger for the PMOS. The VGS was 1.15 for the PMOS, but the threshold voltage was 0.9. So what can I say about the GM of the PMOS here? It's the same. And that's a common thing. When you look at analog schematics, you will often see that they will make the PMOSs 2 to 3 times bigger, depending on the transconductance parameter, than the NMOSs, so that you have the same transconductances that you have for the NMOS. Okay? There's nothing, I'm not doing anything that isn't common here. All right, so we're almost done. We're going to go redraw the schematic to look like the following. The gate drain connected PMOS is going to be a resistor of 1 over GMP. If I wanted to be precise, I could put in parallel with R out P, and that's approximately 1 over GMP. How much AC current flows through here? None. Does everybody see that? Okay, so I'm going to do my AC circuit without that current source here, and then we're going to discuss that to make sure you understand. Because remember, this is just a model for the AC part, but the circuit overall has a DC and an AC component. So I come up here, and I put a resistor here of 420 ohms. And then this gate's at AC ground. This gate's at AC 1 millivolt. Does that, I always get this question every semester. This, you said this VGS and ends up being a half millivolt. How can that be a half millivolt? That's less than the threshold voltage. That device has to be off because there's only a half millivolt there. Why does that not make sense? It's an AC circuit. We're assuming we bias up with the DC, and then once we're at the DC, we've turned the faucet on. Then once we've turned the faucet on, we wiggle it back and forth. We don't say, hey, the faucet's off and you're wiggling it back and forth. How come there's no water coming out? It's assumed that you're biased up there where there's going to be water coming out, and you look at what happens just for the case when you move the faucet back and forth. Okay, so I'm right here, and I go, all right, here's my circuit for AC. DC-wise, what's the current flowing in each branch? 20. So now, if I say the AC current in this is plus 1 microamp, where does that AC current flow? If I say a current flowing in here is 1 microamp, what ends up happening? There's no place for that current to flow but backwards through this device. Well, wait a sec. Current can't flow from the source to the drain of an NMOS. That doesn't make any sense. Wait a sec. If this current goes from 20 to 21 microamps, this current goes from 20 to 19 microamps. There's an overall decrease in the current flowing in this side because I know this current plus this current has to sum total to what? 40. So when I say an AC current's flowing backwards through here, that means there's really not an overall current that's flowing from the source to the drain. It means that the current in this device is decreasing. Does everybody follow that? So when I say current for AC flows like this or flows like that, if I draw it backwards through the device, it means the overall current's decreasing and it has a negative AC current. Any questions? Okay, so let's talk about this part of the circuit right here. I'm going to call this, now I want you to be able to analyze this because this is a diff amp. It's the input of every op amp, and we're going to design op amps in this class, so you need to understand what's going on. I'm going to call this VGS1. I'm going to call this voltage VGS2. Notice the way I've put it. Here's my input. I'll call this 1 millivolt, just like that. I'm going to write a KVL going across. So I write, just so I complete the circuit because I'm learning, I'm going to draw the circuit that I'm writing just like this. And I write, okay, power up, plus to minus to plus, 1 millivolt, minus VGS1, plus VGS2 equals 0. Or VGS1 minus VGS2 equals 1 millivolt. Is everybody cool with that? Okay, so here's the thing. I just intuitively said the AC current flowing through here has to equal the AC current flowing through there. But that can only happen if these two VSGs are equal and opposite. But I want to think about this in several different ways. First, I'm going to go up here and write the equation we always forget. ID equals GM VGS, or VGS equals ID over GM. Would everybody be okay with me writing this as ID1 all over GM1 minus ID2 all over GM2 is equal to 1 millivolt? What's that? Okay, would everybody be okay with me saying ID1 equals ID2? So let's pause on that one. Someone asks you, you go to job interview at Linear or wherever, and they ask you, why does ID1 have to equal ID2 in this diff amp? Here, why does this current have to be equal and opposite to this one? It's very easy. If the current in this one goes up or down, you have to have an equal and opposite amount of current in this one, because the current that leaves both transistors has to sum to a constant, in this case 40 microamps. This goes up by a microamp, this has got to go down. This one goes up by 2 microamps, this has got to go down by 2 microamps, because they always have to sum to the constant current. A decrease or a negative current in here means an overall decrease, going from 20 to 18. An increase, 20 to 21. I don't get confused when I draw currents going backwards for AC. I don't get confused when I have small voltages here for AC. Because I know in an op-amp, these two are basically the same value, so the VSGs are going to be very close to each other all the time. Any questions? Yay? Okay, so one other thing I can say here based upon this and this. Tell me what it is. Well, ID1 equals ID2, but what can I say about VGS1 and VGS2 then? Yeah, VGS1 equals minus VGS2. Which in this case, does anybody not agree with that? If I have an equal current flowing in each of these that's equal and opposite, that, and let's pause and make sure we understand that, then the VSGs have to be the same. If I'm thinking of my yard example, and I stand in my yard and I turn my knob a little bit and a little bit of water changes in it, the other one I have to turn it the opposite way to absorb that extra water so the overall amount is constant going down. So those VSGs have to be equal and opposite. Turn one on more, turn on the other less. Okay, so if I look at this, any questions? These are really fundamentally important things we're going to be using over and over again, just like the gate drain connected for the biasing. Okay, so let's intuitively discuss this. If I drive this voltage up towards 1 millivolt, don't tell me any numbers right now, but what has to happen to the pressure right here? If I pull the pressure here up, it causes what to happen to the current in here? I'm turning this one on more. This current goes up. That causes the change. There's no change in current going down, so that increase in current pulls, or the pressure pulls this node up. Does everybody agree with that? If it pulls this up, this node's not moving anywhere because it's 0, right? So if this node gets pulled up, what happens to this transistor? Starts to shut off because its gate's staying at 0, but its source is moving up, meaning VGS is getting smaller. Does everybody understand that? Okay, so if I go up to 1 millivolt, we'll put the actual numbers in here in a second. This will go up to 1/2 millivolt, meaning what's the VGS here? 1 millivolt minus 1/2 millivolt, which is 1/2 millivolt. This is 0 minus 1/2 millivolt, which gives me a VGS of minus 1/2 millivolt. Does everybody follow that? Is it clear? Okay, so let's go now that we have this, and let's calculate all the AC currents and voltages, remembering our GMs are 150 micro and this was 420. Just out of curiosity, what's 1 over 150 micro amps per volt equal to? So that's what this resistor is equal to. Any questions? Yeah. No, I'm really good at doing simple mathematical calculations. Like I know what 1 over 2 pi times 1 millisecond is. 159. All right. Okay, so let's redraw the schematic. Here's the gate drain connected transistor. It's 6.5K. Here's my one transistor. It's got a gate that's 1 millivolt. This is 420. I'm going to call this V drain 2,4. And I'm going to call this V drain 1,3. And then this is AC ground. Okay. I'm going to be a little bit different. I'm going to call this current ID1. And I'm going to say this current here is minus ID2, which equals ID1. Because ID2, by definition, is the current that flows from the drain to the source. And so the current here flows around like this, which I know just means this current goes up, this one goes down, this one goes up, this goes down. Any questions? I'm going to write this voltage here, knowing these VGSs have to be equal and opposite, as 1/2 millivolt. So I'll write this as 1/2 millivolt. The voltage from here to here is 1/2 millivolt, which means V gate source equals 0 minus 1/2 or minus 1/2 millivolt. Everybody cool with that? Okay, so then I go back and I say, all right, what is the current that flows here? GM times VGS, 150 micro times 1/2 millivolt, which equals 75 nanoamps. Looking good? What's the current that flows here? 75 nanoamps. It's got to be the same. So this current, if I were to write it, is equal to 20 microamps DC plus 75 nanoamps, assuming this is a peak, times cosine, whatever, sine or cosine doesn't matter, 2 pi times whatever F is times T. And this current would be minus 75 nanoamps, so that they would always sum to 40. Any questions? All right, what is this voltage, VD2, for? Gee, you're not challenging me. You got 75 nanoamps flowing in 420 ohms. It's just 420 times 75 nano, which is what? 420 times 75 E9 change sign equals 3.31 microvolts. 31.5 microvolts. Any questions on that? Okay, I've calculated every AC voltage and current except for which one? This one. The current's flowing backwards through there. So the current's going up from ground. So that's equal to minus 6.5K times 75 nanoamps, which is 6500 times 75E9 change sign equals, what is that? 1/2 millivolt roughly. Done. Any questions? Ten minutes. You have a homework problem that's just like this one, except they changed the currents a little bit. Okay? All right, so let's look at the SPICE real quick because I want to make sure we can all do that, and then we'll talk about small signal models, and then this class gets over at 2:15, but since I started class 4 minutes late, we'll quit at 2:09. No, I got a pen. All right. Let's go to 9:18. Let's see what this is first. All right, so I want to just look at what I was talking about here. So I'm going to do a dot operating point, and I'm going to hit run. This voltage I said was 4.99, 4.89. Okay, current flowing in each one. Oh, here's a good finer point question. If I look at the DC current flowing in M1, it is 19.88 micro. And if I look at the current flowing over here, it is 20.11. In other words, the current flowing in this device is slightly higher than the current flowing in this one. Why? Okay, are the VGS's DC any different? If I put the VGS here, I get 2.5. If I put the circuit here, I get 1.175, a little bit lower than what we calculated because of the body effect, and here it's 2.5. VGS's are exactly the same. Why? This is what tells you if you have some depth of knowledge or your knowledge is fluffy. Why is this one has slightly more current flowing in it than this one? And we're going to use this little thing over and over again. First thing I talked about today, what was it? Answering Kobe's question. Output resistance, right? What happens as VDS is increased to the current flowing in the MOSFET? Forget impedance, just real simple. In terms of current, if I increase VDS, what happens to the current? Goes up. Well, here, this voltage is almost 5 volts. This one's 3.85. So this transistor has a smaller VDS than this one. So I expect this one to have slightly more current flowing in it than this one, and it does. So when we're trying to get good matching, which means have two currents and two devices behave electrically the same, one of the key things we're going to focus on is trying to equalize the drain to source voltages. So nowadays when you do designs, you're doing things like, say, at Qualcomm, and you're using a 15 nanometer process, the matching, because those devices are so tiny, they're just like, you can literally count the number of electrons underneath the gate channel, or in the channel, or the number of atoms used to manufacture the device. The matching is super critical for yield and performance. Okay, if things don't match, especially in the analog circuits, you don't get good performance. Like in your displays or your listening devices or those things. In the digital, it's much less of a problem, but for the analog, it's a big problem. And so you need to know to equalize the drain to source voltages. That is the most important thing for matching. If you don't do that, nothing matches. Okay, any questions on that? So if you were to go and someone were to give you this circuit and they say, why does this current have slightly less current, this transistor have slightly less current than this one, everybody could articulate the VGSs are exactly the same. Both gates are at DC 2.5. The sources are physically wired together. So this one has a slightly smaller VDS than this one. This is, think in digital terms, this is just an on device. Its gates at ground. It's trying to pull this node all the way up. So its VDS is bigger. Any questions? So let's look at the AC now. Okay, so what did we calculate the AC volt? Let's run it and see. Boom. Let's just look at each one. What did I say the voltage here would be? 1 millivolt. The voltage here? Half a millivolt. But now, again, we have the little body effect that changes things, so it'll be off a little bit. Okay. AC current flowing in here, 75 nanoamps. It says 71. My transconductance is off a little bit. 71. And if I go do the dot OP again and I look at my GM, I'm going to see that it's slightly less than, I keep saying that, the body effect. Is anybody confused by that? If I say this, because of body effect here, we have slightly lower. So for example, we calculated this as 2.45 DC-wise, or 1.45, and it's 1.17. Why is it lower than what we calculated by hand? Don't say body effect. Yes, it's body effect. Well, the threshold voltage goes up. When the source and the bulk aren't tied to the same potential, you steal charge from the channel and it raises your threshold voltage. If the threshold voltage isn't 0.8, it's 1, then obviously this node voltage for 20 microamps flowing through it is going to go down. Does everybody follow that? Okay, where do you go in the book? So he keeps talking about body effect and I'm totally lost. Where do you go in the book to get a qualitative description of body effect? Chapter 6, right here. Here, if you look at this, if my source and my bulk are not at the same potential, the bulk steals charge from the channel. In order to invert that surface, I've got to apply a larger VGS here, which means my VGS goes up, my threshold voltage goes up, because the body steals the charge from the channel. Very straightforward issue. Any questions? All right, let's look at a couple more, then let's look at the time domain, then let's move on. Okay, current over here. Oh, we just did that. Voltage here, we calculated 31 microamps. Here it gives us 36. What other signals? Oh, we looked here. This was half. We calculate half a millivolt. We got 416. Am I missing anything? Okay, this is just showing magnitude, correct? Let's go show the overall currents and voltages, both AC plus DC, because AC sweep only shows the AC. Any questions? Okay, give me an example where a circuit that you've used already, where this voltage and this voltage will be the same on the input of a diff amp like this. Give me a circuit that you've used since circuits 2, or maybe even circuits 1, but you weren't in the lab. That the input here would be equal to the input over here because of feedback around the circuit. I don't know how much more leading I can be. What is it? You look tired, man. Too much Super Bowl. I gotta do CMOS. Stop the Super Bowl. Don't tell me who won. My homework's not done. He's not assigning enough tedious homework. All right. Give me an example. Where would I have a circuit where this voltage and this voltage are the same? An op amp. This is the input of an op amp. There's no magic here. You're going to know how to design an op amp by the time you get through with the class. It's not going to be magic to you. All right? What's that? Okay, so let's go back and look at the AC. This is the same thing except I put sine wave in, 1 millivolt. And I run the sim, and there's my, let's look at my input. Does that look correct? DC's 2.5, magnitude's 1 millivolt. I go over here, and I see a DC of 1.17, and a magnitude, let's see, how can I figure out what the magnitude is? Yep, subtract 1.7, 17. Wait, what is that? Minus 1.1712. Yep, that's pretty close. And that's, again, not all the way to half millivolt because of the body transconductance. Here, if I plot the current or the voltage, I get AC is 0. If I look at the current that flows, I get my 19.89. Let's see what happens if we remove that. What was the magnitude of the current, roughly? What was the magnitude of the current I calculate? GM-VGS. 75 nano. Okay, I know what I'm doing. If I go look at the voltages, this was roughly half a millivolt, and I'm not going to subtract. You can just say, oh yeah, it looks half a millivolt from 0 to 4. And here was 35 microvolts. And you could subtract that out and look at it that way. But that way we look at the transient, we get just AC and DC and the AC and then the dot operating point. A lot of concepts in that example. Are there any questions? All right, so I want to talk briefly about body transconductance one more time. Actually, you know what? Let's not. Let's move ahead to small signal model and talk about FT. And the next time we'll come back and talk about the body transconductance. Everybody followed that example. Everybody read it this weekend. Super Bowl, no. Example 9.5, yes. Okay. All right. So, let's sketch our small signal model. Here's my gate. Here's my drain. Here's my source. Tell me what to connect between the source and the drain. R out? What's R out equal to? What else do I throw in there? Current source. What's that current source's value? Because I have this current, that's ID, but then I also have a current due to the output resistance. So the overall current's not going to be exact because I also get a current flowing through the output. Then I come over here, this is still my source, and I label this voltage what? VGS. Now in a moment I'm going to put capacitors in there, but before I do that, I want to prove that a gate drain connected transistor has a small signal resistance that's approximately 1 over GM. So I want you to tell me how to prove that. Okay, let me make a mistake. Say I give you this on a take-home test or quiz or something. I say, prove that the gate drain connected transistor has a small signal resistance of 1 over GM. And you say, okay, well I know to do small signal analysis I got to bias it up right. So I'm going to go do the following. I'm going to put an AC signal here, let's say 1 millivolt, and then I'm going to put a DC current of 10 microamps. And I ask, okay, I want you to think about this. What is the AC voltage here, VGS, and why? Okay, what's the drain current flowing through here? Okay, this is a trick question. It's a trick question because I got a current source right here, right? The current in that circuit's always 10 microamps. I can never change it. So if it's always 10 microamps, what can I say about the AC VGS or how much this VGS changes? It doesn't, because the current is always constant. But wait, I have a voltage source here. Where does the changing voltage source, if this voltage isn't changing, it's always fixed, it's say 1.1 volts, and I would calculate it based on the 10 microamps flowing through the device. If it's always changing, and I have this 1 millivolt, where does that voltage drop go? Where does this 1 millivolt change occur? Yeah, right across here. Does everybody see that? Okay, so I'm going to change this because this doesn't work. I don't want you to feel pain, so you need to understand why that's the case if you have to show that this is the resistance. So I'm going to replace this with a voltage plus minus. I'm going to call it VGS. Looking good? How do I calculate the current that flows? Oh, it's ID equals KP. It's always come back to this equation. Even before, when I had a constant current, it would come back to this equation, and I'd solve for VGS. W over L, VGS minus V threshold N squared. And now I ask, all right, if I got a current flowing in there, what is, if this is a voltage source, what is the AC voltage here? 0. What is the AC voltage here? 1 millivolt. And if I write the KVL, plus, minus, plus, plus, minus, sums to 0. Any questions? So I go back to my model and I say, okay, I need to replace the model. I'm going to write this circuit and I'm going to use the model. I'm going to write the following. Gate being connected over to the drain to R out to GM VGS going here to ground, and then over here I have 1 millivolt, which equals VGS plus minus plus minus. Would everybody agree VGS and VGS are equal? Okay, so now I've got a question. If I want to find what the equivalent small signal resistance for this device is, tell me what to do. It's the current that flows here, let's call I total, divided by, or divided into, this V test. It's the voltage here, V test, divided by the current that flows in the device. We're going to do this over and over again. What's the input impedance? Apply a test voltage, look at the current that flows in the test voltage. Apply a test voltage, look at the current that flows in the test voltage. That's divided into the voltage as the impedance. So I go back, any questions on that? I go back over here and I go, okay, what's this voltage? Let's call it VT, just to be, we'll call this IT. So we got VGS equals VT equals 1 millivolt. What's this voltage? It's 1 millivolt. I'm physically holding it at 1 millivolt. Anybody not see that? So if I write I test is equal to 1 millivolt, V test, divided by R out. Plus the current flowing in here, which is what? GM VGS, or I'm going to skip it because we're running out of time, GM V test. Or I can write V test over I test, which is the impedance looking into the gate drain connected device, is equal to 1 over R0 plus 1 over GM, which is equal to 1 over GM in parallel with R0, which is approximately 1 over GM. Because any usable transistor, 1 over GM has to be less, much less than R out, or you don't get any gain. We'll see that later. Any questions? Does everybody see how I did that? So, in the future, when I say this transistor is equal to 1 over GM, you go, yes, and I know how to derive that. That would be a good quiz question for Wednesday, if we have a quiz. Getting them every day. I know you like it. But it eats a lot of class time. Any question? All right. It's all clear? All right, so when we come back, we'll talk about other stuff. Let's take our little quiz.